Introduction to hypothesis testing. Two numbers may look different, but considering expected fluctuations, how do we determine if they are statistically equivalent? This is where hypothesis testing comes in. It helps us decide whether the numbers are truly the same or not, in a way acceptable by convention. Now, before we go into hypothesis testing formalities, a quick word. If you're in school or university studying statistics, kind of go through the formal test of hypothesis that will be discussed here. However, if you're here for the applied side and going through the boot camp on statistics for data science, the more interesting part would be how practitioners actually use the test, and that's what we're going to focus on here. In real life, you would be using software that will show you some output. In our old example in lesson 1, maybe we'd like to find out if the two means from set A and set B are in fact statistically the same. If they are, then the difference between the two averages should not be significantly different from 0. So we might want to test if the difference is in fact not significantly different from 0. So an output from an Excel t-test of equality of means is shown here, and we make the hypothesis that the two means in our example are statistically the same. Now, what exactly might this output mean? Now, given this output, we say that the mean difference is not significant, meaning it's not different from 0, and therefore the two means are statistically the same. So at the end of this video, we will explain to you how to come up with this kind of output in Excel, and more importantly, how to interpret the results, thereby doing the quick hypothesis testing that practitioners do in real life. The logic behind the test. When we have a research problem, we might want to come up with a testable hypothesis called the null hypothesis, or just H-null, that we can accept or reject on the basis of some agreed upon convention. This implies that when we accept or reject the hypothesis, it is relative to a convention, and we are in fact accepting that there is still some potential error in our decision making. Now, there are two kinds of errors that we can make. Type 1 error is rejecting a true null hypothesis or a false positive. The associated probability is called the alpha, also known as the level of significance. We also have the type 2 error, accepting a false null hypothesis or a false negative. The associated probability is called the beta, that is 1 minus the power of the test. In medicine, for example, the null hypothesis might be, well, people don't have the disease. Now we might conduct a test, and if a computed probability, let's call it the p-value, falls below a threshold acceptance level, say 5%, and let's call that alpha, or level of significance, then the null hypothesis is rejected for failing to reach that acceptance level. So if the p-value is less than alpha, we reject that null hypothesis. If so, this means we reject the statement, people don't have the disease, since the p-value is so small that this kind of event is rare enough to happen just by chance. So it must not be chance anymore, and there might be something different happening here. However, there is still a potential error in so rejecting the null hypothesis, which is a type 1 error. Meaning, there's still an error that the person tested doesn't really have the disease but just had a false positive, and this is our alpha. By the way, the p-value is not the probability that H-null is true. It only tells us how extreme the data is if H-null were true. Okay, now what happens when the null hypothesis is rejected? Then there must be an alternative hypothesis that now becomes activated if the null hypothesis is rejected. So if the null hypothesis is that people don't have the disease, the alternate hypothesis is people have the disease, or at least some people. Note, to reduce type 1 error, we can try to accept everything, be gullible, and don't reject anything. However, doing so will make us fall into the second type of error of accepting a false hypothesis. So to reduce a type 2 error, we can try to reject everything, be cynical, and reject everything. However, we fall into the first type of error. So there has to be some sort of balance over here because we can go around in circles. Now, we're ready for the steps in hypothesis testing. What are the steps in hypothesis testing? Number 1, state the null and alternate hypothesis. Number 2, select the level of significance, usually 5% or 1%, and has to be selected in advance. Number 3, identify the test statistic. Is it an F test, a Z test, a T test, etc.? Formulate a decision rule, meaning if the computed statistics falls within the number of standard deviations of the acceptance region, then we accept the null hypothesis. Step 5, calculate the statistic and make the decision, meaning accept or reject the null hypothesis. Visualizing the test. If alpha is 5%, and we're talking about two extreme events on each side, or two tails, then we divide alpha by 2 and cut 2.5% on both sides. The acceptance region becomes 95%, and this is roughly 1.96 standard deviation to the left and right of the mean. And if the computed statistics falls within this acceptance level, then we accept H null, but otherwise we reject it. Going back to our example, let's take a look at the z-test of the equality of means output. The null hypothesis is the difference between the two means is 0. The alternate hypothesis is the difference between the two means is not 0 on a two-tailed test. Let's use a level of significance of 5%. The test statistic will be the z-test for the equality of means. And we will formulate a decision rule. If the computed z-statistic falls within negative 1.96 to positive 1.96 standard deviations from the mean, then we accept the null hypothesis. Then step 5, we calculate the statistic and we make the decision. Here we note that the computed z-statistic is negative 0.0537, and with an alpha of 5% or 0.05, then the acceptance region falls within negative 1.96 to positive 1.96 standard deviations, under which the computed statistic lies. Therefore, we accept the null hypothesis and conclude that the means across the two samples are not statistically different from each other. In practice, however, hypothesis testing often comes down to the p-value and how it compares to the alpha or level of significance. The factors like study design and sampling are also important. Assuming everything is properly set up, the key focus is usually on the p-value and alpha. If the p-value is greater than alpha, then accept the null hypothesis, and if the p-value falls below the alpha, reject the null hypothesis. In our example, the p-value is 0.957 and way above the alpha of 0.05, so we accept the null hypothesis. In this Statistics for Data Science course, we will focus more on testing if coefficients are not significant. So we usually do a two-tailed test if the mean is equal to 0. Normally, we just compare the p-value versus the alpha that we established prior to doing the test. This is what the hypothesis testing would look like. The analysis of variance. For future linear regressions model, an ANOVA table is usually provided to understand if the means of two samples are actually statistically the same or not. While the analysis is on the variance, this is actually a test of the equality of two means. The motivation for the ANOVA. If two sets have the same means, getting the variance of the two sets and putting them together versus mixing up the set as one, then getting the variance of the pooled set should be substantially the same. This boils down to comparing the variances of the two sets, but rather than getting the difference between the two variances, we divide one variance by the other, and if they are not significantly different from each other, they should be almost the same, then the ratio should not be that different from 1. So if you found this helpful, give this video a thumbs up and let us know in the comments what you'd like to learn next. See you next time when we talk about machine learning and linear regressions.